Okay, we have a transformer. Transformer is used in a hydroelectric power plant to step up the output from a 720 megawatt generator. The generator operates at 60 Hz, 18 kilowatt. The output voltage required for transmission is 750 kilowatt. If an ideal transformer is used, calculate the turn ratio and input and output currents at full load. So, how do we proceed with the first question?
As the first, we U1 divides U2 is equal E1 E2 divide E2. We use this form.
Schematisch kerak
E1.
Okay, first.
Yo, I1 topish uchun mana P teng IU bor-ku. Hozir quvvat bor bu yerda, kuchlanish bor. Biz bundan current topsak bo'ladi. Current 1 topamiz. Shunda keyin uni formulaga qo'yib, current 2 ni topib olamiz. Keyin o'sha formulaga asosan, aylanishlar sonini ham topsak bo'ladi.
So this is the primary coil, secondary coil, N1, N2, V1, V2, and I1 and I2. Okay, you are saying, please repeat.
Ustoz, hozir bizda V1 bor, V2 bor. Keyin I1 ni topsak bo'ladi currentni. P teng Udan topsak
I1 equal to
bittasi U.
UR.
V divides U.
Power divided by V1. Yes?
U. V1. Yeah.
Okay. Power in our case is 720 megawatt, 10 to the power 6, over V1 is 18 kilowatt.
18. 4.
5.
40.3.
5 or 4?
Yo, 4.
4. Of course, 4. 10 to the power 4. Sorry.
4, yeah.
Oh, 4. 4. 10 to the power of 4. Okay. Great. We found I1.
Yeah.
Now
we put transformer form borku ale transformator form.
What about I2?
I2'da endi I1 taqsim I2.
Okay, look. For the ideal transformer, power transmitted doesn't change. P1 is equal to P2 for ideal transformer. So the I2 will be P over V2. Yes?
Yeah.
Yes, did you understand this?
Yeah, I understand.
Okay. It means that power is again 720 megawatt 10 to the power 6 divided by the output voltage required for transmission is 750 kilovolt is equal to 72 by 75. Okay. $960 ampere. Yes?
Yeah.
Multiplied by 3. Okay. What about the turn ratio?
Generation.
Turn ratio is
Gers turibdi-yu.
N1 over N2. N1 over N2.
Is equal E1 over E2.
Sorry?
E1 over E2.
You mean current 1 over current 2? You mean this?
Yeah.
No. Turn ratio was, okay, primarily was V1 over V2 or I2 over I1. Because turn ratio N1 over N2 is equal to V1 over V2 or N1 over N2 is equal to I2 over I1. Please don't forget and don't confuse. So, okay, V1 over V2. So turn ratio is A is equal, we said V1 over V2, which is 18 kilovolt over 750 kilovolt. Okay, which is equal to 18 over 750. Zero point 0.024. This is our turn ratio. Okay. We go to the next question. Ideal transformers don't exist. Suppose the transformer has 1% losses. Calculate the required turn ratio to maintain an output voltage of 750 kilovolt at full load. Assume all power loss occurs in the iron core of the transformer. Okay. If we have the loss of 1%, it means that eta will be 0.99, and for simplicity we assume that all losses occur in the core of transformer, and so the turn ratio N1 over N2 will be eta V1 over V2 and 0.99 multiplied by, okay, V1 over V2 was 0.024. is equal to so 2.376 10 to the power of -2. Okay, this is our new turn ratio, and 1 over n2 we said 2.376 10 to the power of -2. This is very rough simplification. Okay, this expression is a very rough simplification. So if we go to the next, okay. No, I think we cannot write. No, it's okay. 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 You have the third part of the problem. Well, where is the problem? Yes, you have the third part of the problem, part C. Try to do this by yourself. It is also not so difficult. You use the you use certain formulas and compute. You can compute the output current in the transformer. Okay, well, so magnetic brake, DC motor, the watt meter, rail launcher, so one of the interesting applications of the Faraday's law and electromagnetic induction is you may see here the rail launcher. So well, it consists of two parallel rails. This is the first rail and this is the second rail, and in between them there is conducting material, which in this case is called as a projectile. And when you apply current to the lower rail, okay, not current, sorry, when you apply electric motive force to our rails, current start to move in this direction, and besides that there occurs, well, when current starts to flow in our rail, there occurs magnetic flux density between our rails. You may see the, okay, this is the isometric view. You may see here the side view, and current coming in the upper rail, current coming to the direction towards us, and in the lower rail, current going towards the plane, and there occurs a magnetic flux density B because of flowing currents. And let's move back to the picture A. And in the picture A, we can see we called projectile. Projectile, we said, is a conducting material, which is free to move in between two rails, and when current flows in this direction, current also flows in upper direction inside our projectile, and as current flows inside our projectile, this magnetic flux density B starts to push our projectile in the, okay, starts to push our projectile, and our projectile starts to move. This is the very case when we see the problem. If you remember, we had two rails with some resistances, and one bar which is free to move in the rails, and the end of rails are connected to the voltage source V, and this is situated in some magnetic field with flux density of B. When current starts to move, this bar, okay, some force will act to this bar, and this bar starts to move. Here in a rail launcher, it is also called as rail gun. The same effect is used, and the same effect gives some acceleration to our projectile. Well, this method has been used to demonstrate the possibility of firing the projectiles at velocities much higher than it could be possible with explosive methods. And this method, well, this method can be also applied in, for example, military actions, or maybe in space. Can be used in space for launching the satellites to the orbit. Okay, the principle is very simple, and is the principle of this railgun is, okay, you can see in this scheme. And well, one other application is, so one other application of, okay, electromagnetic induction is magneto-hydrodynamic generator. It is a DC generator. The principle is that of a moving bar in magnetic field Uh, um, okay, and in this case, instead of moving bar, is used conducting fluids which move between two conducting electrodes. Okay, as shown here. Some conducting fluid, maybe I don't know, water with some salts can be conducting fluid, or some oils with salts can be also conducting fluids. And these conducting fluids move between two conducting electrodes, well, as shown here or here. So two magnets which are, okay, placed here and here. Two magnets generate a very high magnetic field in a channel between them. So we put one magnet with north and south, and another magnet with, so vice versa, south and north, and magnetic field lines go like this. and these two magnets generate very high magnetic field in channel between them, and this channel is okay, sometimes it can be called as magnetohydrodynamic channel, and two conducting electrodes are placed at right angles to the field, insulated from the magnet and each other. So, if we look to this picture, which is the picture B is a side view of picture A, and okay, this is one conducting electrode and this is another conducting electrode. These are our magnets. With north and south and north and south, and these are the magnetic field lines. And well, in the first case, fluid was flowing in this direction, V. Fluid is flowing in between two magnets in the magnetohydrodynamic channel. And in side view, fluid is flowing towards us. And okay, and a conducting fluid is now forced to flow through the channel. The magnetic field and velocity product V, so V cross B are as shown in the figure here. Here in this figure, we draw the directions of V and B. Also, yeah, the directions of V and B. And this indicates that the left plate becomes negative and right plate becomes positive. So from this product we can conclude that left plate becomes negative and right plate becomes positive. Well, okay, the principle is more or less the same as it was with moving bar inside a magnetic field. Only in this case, instead of moving bar, we are using the conducting fluid, and this conducting fluid under the when this conducting fluid flow in the magnetic field, it produces well electric motive force, and from this product we can conclude that left side of our electrode will be negative and the right side will become positive. So The conducting fluid can be any fluid which conduct the electricity. Most experimental generators use highly ionized exhaust gases from the burning of fuels. So, okay, instead of water or instead of oils with salt, it can the exhaust gases from the burning of fuel can also be used. Okay, a very simple magnetohydrodynamic generator is made of a channel as above, connected to the is connected to the exhaust of a jet engine. Well, and to increase the conductivity of the gases, these are seeded with conducting ions such as alkali metal vapors. Okay, the others are related to chemistry. And well, the most attractive feature of the generators like this is the fact that these generators are stationary. For example, you don't have moving parts, rotating parts, or I don't know, moving parts, and they produce directly DC current. And however, another, let's say, the disadvantage of generators like this is that most generators like this have low efficiency. The efficiency of the generators are lower than 15%. Okay, but okay, in spite of the low efficiency, system can be fully contained and can operate in closed circuits. Okay.
Xizmlarga biz doimiy magnitlar o'tamiz. Hozir
This is type of generator with magnets and fluid flowing inside this magnetic channel. Well, okay. Let me